Hi everyone, welcome, and thank you for joining me. That's where I wanted to start today. It's great to get to do this, and I'm so happy that people are still kind of tuning in for today's installment of me sitting and staring and talking at my computer, which is something I'm growing fond of. But I thought I'd make a brief note before I start today. So I'm very big on giving students the opportunity to, thanks for the feedback on the mic gain, let me just adjust that. Let me know if that's a little better. I lowered that a little bit, so it should be good. So hopefully that's a little bit better. Oh, still bad. Okay, give me a second then. Can you hear me now? Okay, let's try that. That appears to be at an appropriate level. We were at too low, now we were too high, now we're too low. Okay, so we're good. It's good. I was planning on cutting out the start of this anyway, because I wanted to point out that still a bit low. I wanted to point out that typically how it would work in a classroom is to frequently stop and give students an opportunity to interact with each other, answer some questions that I would pose to people, and kind of have breaks as we go through. And that kind of builds in this active learning classroom where we have an opportunity for everybody to participate and do things as we're going. With this, it's become clear that I have quite a few people who don't watch the videos concurrently. And so for them, if you're fast forwarding or something, it becomes tricky to know kind of how far do I need to go before the silence ends where we've taken a short break. And so to avoid having to do a lot of editing later, I'm going to keep those types of breaks to a minimum, especially because if you're watching concurrently, I would imagine it's in the evening, you want me to kind of get through the material. You can always come back to it and pause things later if there's a moment or something where you want to practice doing something on your own. And so I will keep those kind of breaks to a minimum to make the experience as efficient as possible for people watching concurrently. So with that aside, I'll start what I wanted to discuss today. So there are three things that we want to do. One is I want to estimate the house edge of craps, this binary game that I introduced in the theory lecture, and to do so with this approach called Monte Carlo simulation, where we use randomization to produce an estimated answer. And what you'll see is if we all do this separately, we will get different answers to it, and we would get a very good answer by, say, taking the average of running a bunch of different simulations in parallel. The second thing that I want to do is to come back to simulating an election using Monte Carlo simulation. So can we forecast the result of an election from polling data? And so that's something that I've provided as data sets with downloadable code where you can see polls at 3 different points in time. And we're going to see how those forecasts change as the polls changed for a presidential election. And then the third thing that I want to do is reflect on the nature of Monte Carlo simulation, especially as it's used for forecasting, and see how simulating an election is a slightly different example than doing something like estimating the house edge of craps, because we're dealing with something that's very practical and that is data that's not perfect, whereas when we're simulating rolling a die, we're going to be able to assume that that die is completely fair, that you have a 1 in 6 probability of rolling any number. So with that aside, I would like to start with the problem of estimating the house edge of craps. And so I've got an atom file open, and I'm going to save this file in a new directory. We could call it, for example, craps. It will go in the go src directory. I'm just going to call it my favorite World Series of Dice character, Grits and Gravy, and I'm going to put a main.go in that directory. So this is going to be runnable code, so I'm going to have a package main at the top of the code, and then I'll need my func main, and we'll say that we're doing a crap simulator, okay? So what we've seen on the level of pseudocode is that if we want to simulate craps, then we need to simulate the process of rolling 2 dice, which means that we need to simulate the process of rolling 1 die. And so in Go, we're going to get a pseudo-random number generator that's built in. If we go to the package, use the package math/rand, and it has 3, I'm going to soft wrap the text. It has 3 built-in functions that we'll use a lot. Thought I'd soft wrapped it, but I guess I didn't. Okay, and so the first one is, and I mentioned this on the level of pseudocode, but rand.int is going to be a random or a pseudo-random integer. We're going to have rand.float64. That's going to give us a pseudo-random decimal in the interval 0 to 1. And the third one is going to be rand.intn, and that's a pseudo-random integer between 0 and n-1 inclusively. Okay. And so to access these, I will need to import math/rand, although if I've got Atom set up with Go Plus and appropriate packaging, I won't need to type out that that's what I'm going to import. But it's within the math package, and if you follow it along with the theoretical discussion of PRNGs, now we understand why it would come from the mathematics package, because why RAND would be a sub-package, because it is very mathematical work. Okay, so we need to know math in order to understand how PRNGs work. For now, I want to show how these built-in functions can be used. So we saw that one simple function for, say, rolling a die. So if we want to roll a single die, it's not going to need to take any input parameters, but it should return an integer. Then we could simply call rand.n of 6, which is going to give us a random integer, or I should say a pseudo-random integer, between 0 and 5 inclusively, so it gives us 6 options. And I want a number between 1 and 6 inclusively, so if I add 1 to that result, I'll get what I need. And so we've used our RAND package now, and I could, for example, call this. And I pointed out in the pseudocode discussion that we could write this function in a variety of different ways. So for example, I could call rand.int and percent it by 6. So that's the remainder when a random integer is divided by 6. That would also give us an integer between 0 and 5 inclusively. That's actually how rand.int n is written. It just percents by n. But the easiest way to think about this is generate a random integer between 0 and 5 and add 1 to it. Okay. So what I would like to do then is, why don't we have a few die rolls? So we can do, I don't know, 7 die rolls. And each time I'm just going to print the result of rolling the die. So if I save this, and if I have a terminal window, I can cd into the appropriate location. So this was go src, and in specific I had called this Grits and Gravy. You could call it craps. If I compile and run, then you'll see 7 die rolls. And the first thing that I would point out is, okay, well, let's see what happens when we do this again. So if I run the function again, presumably I would get a different set of die rolls. After all, isn't this supposed to be a random process, or a process that's mimicking a random process? Well, we happen to see the same exact sequence of 7 rolls. I could do it again. Maybe it's just random chance, but every time that I do this, I'm going to get the same sequence of 7 rolls. Okay, so this is more than just coincidence. And the question becomes why this might be happening. So we learned with our work on pseudo-random number generation that if you have some pseudo-random number generation process, you need to start that process somewhere. So for the simplest, say, middle square approach, we needed to start with an n-digit number, and that number was called our seed. For any pseudo-random number generator that we produce, we're going to have some seeding process, meaning that the generation has to start at some point. And once we've selected that starting point, then we can produce additional pseudo-random numbers. So if we want a different sequence here, for this case, at least for now, I could use a function called rand.seed, and that is a function from the rand package that calls seed and that needs to take an integer input. So I could give it, say, rand.seed of 100. And now if I build and run, I will get a different sequence of rolled dice. The point is that rand.seed only needs to be called once, because we only need to start the pseudo-random number generation once. So we could be generating millions of numbers, but we would call rand.seed once. If I called it on, say, rand.seed of 0, we'll see that this should change things. If I called it on rand.seed of 1, we'll probably get a different sequence. And that's actually the original sequence that we had. So 1 is the default value that if you don't call rand.seed, default value of seed is 1 if the rand.seed is not called. But this is not really what we want. We don't want to have something where every time we run a program we get the exact same sequence of integers. What we want is something that appears random. It doesn't have to be random, but it should seem random to us. And so it seems like a catch-22. How can we provide a seed to a pseudo-random number generator if you want a different outcome every time that it runs? Can we somehow seed the random number generation process randomly by letting it start at just kind of an arbitrary point? And then if you think about that, isn't that just as difficult as the problem of generating random numbers to begin with? And so there's going to be a way around this by seeding based off of going far enough out in the current time where we're on kind of the nanosecond scale. So if we go far enough out in whatever the current time in the computer is, those numbers are rolling over so fast that we probably wouldn't be able to run a program so quickly after it has already been run that we would have only increased the number of nanoseconds by a bit. So for our purposes, if we look at kind of the round off or the last few digits in terms of nanoseconds on the internal timer of the computer, then that will be a natural way for us to seed the random number generator. And when I say random number generator, I always mean PRNG, but we view it as how they look to us. The numbers are looking random to us, and that's what we care about. So I can import the time package, and I always have one line of code that I would never remember, but I always would have handy, which is that I can, I'll say, instead seed off the time. So if I comment that out, I can call rand.seed and then call time.now and grab the nanosecond scale. Okay, and I'll explain this type of writing functions soon as to kind of how this syntax should work. We know that we're in the time package, but why is it that we can do time.now and then .unix nano? What is the notation that's going on there? For now, I'm just going to remember that any time that I want to seed a random number generation process randomly, I can just use that one line of code exactly once, and put it in the main function, and then however many different functions are needing the PRNG, the random number generator has been seeded, and so from that point forward everything is going to seem random to us. So if I've seeded based off of the time, and now I compile my program and run it again, I'll see a different sequence, and if I compile it and run it again, I'll see a different sequence. That one actually wound up being pretty similar, but it's just, at least on my machine, but it's just random chance. And so every time we compile and run, I don't need to compile this every time, because every time I'm seeding off of the time. Okay, and so you'll see we're getting truly different sequences of random integers. So that's going to be all we need really for the gritty details here, because once we can roll a single die, we know that we can roll 2 dice. And so rather than needing to delve into a mathematical table, I can write a sum 2 dice function that returns an integer. And so I should be true to form here in terms of being stylistically sound, and comment the function and say what it does. So we'll just recall that a sum 2 dice function takes no inputs and returns the sum of 2 simulated 6-sided dice. So no input is going to be taken here. We're going to produce this integer based off of the sum, and the natural way to do this would be to say we roll the die, and we roll the die again, and we take the sum and we return it. So using modularity there, and now we've got our function for summing 2 dice, and I'm going to skip down, and I could test that of course, but I'm going to skip down and say, well, remember that we've got 2 functions to write. We have one function that should be called play craps once. So I should say play craps once takes no parameters, so no input parameters, and returns, well, it's going to return a true or a false depending on whether we win or lose, so depending on the outcome of a single simulated game of craps. And here's where we could go back to the pseudocode level, because this is something that we've planned on the pseudocode level. It's just a matter of converting to the programming language of our choice. And this is going to return a Boolean. And so here's where we said, well, we have a first roll, and that's a variable that's equal to the sum of 2 dice. And then we have a couple of initial tests. So we need to say, is it the case that we won initially? Well, that's if we hit a 7 or 11. So if first roll is equal to 7, or that first roll we hit an 11, then we're going to return true. Okay, that's an immediate winner. Else if that first roll is equal to, and here we say, well, there's 3 losers. And I would point out it's easy to just to write it that way, but we need to be precise with our tests. So we need to check, is it the case that first roll is equal to 3, and is it the case that first roll is equal to 12? So all of these are going to be losers. And then we don't technically need an else, but it will help us reason through the fact that, well, in the third case, we're going to roll again. So if we roll again, we're going to continue rolling forever, for as long as it takes until we hit a 7 or our original roll. Okay, so we could be at the table forever, and for that reason, it makes sense to have a function that reflects that structure. So it seems like it might be an infinite loop or bad style to do something like while. I always forget that Go's keyword for while is 4, but while true, so this just means loop forever until we either hit a 7 or our original roll. And I'll have to make sure that the code inside of that loop is correct, or else I'll produce this infinite loop. And so we know that, well, we've got a 4, 5, 6, 8, 9, or a 10. And so we'll say, for as long as this happens, we're going to roll again. So we sum 2 dice again, and I'm going to take whatever that output is and put them in a new roll variable. And here's where we say, well, is it the case that new roll is equal to our original roll? And in this case, we're a winner. So that would be good. And so we should return true. It would be tempting to say else, but it's an else if, because it's not in all other circumstances that we're a loser. The case that we're a loser now is if new roll is equal to 7. And in that case, we are a loser, and we should return false. So there's our function to play craps once to return true for win and false for a loss. And I'm going to try and move this over a bit just so that you can see the code a bit better. And because once we have this play craps once function, it's just a matter of writing the function that calls play craps once. And that function that calls play craps once is something that I had called compute house edge. And it takes a number of trials as an integer. And so compute house edge takes an integer, num trials, and returns an estimate of the house edge of craps, or whatever binary game. I could generalize this to play an arbitrary binary game or play one of 4 different possibilities, and simply substitute out play craps once for play that other binary game one time. And so it's going to return an estimate of the house edge of craps played over num trials simulated games. And so what it should return is a decimal number. And here's where we say, well, first we use count to keep track of how much money that we've won or lost. So here's where we're assuming that we're wagering a single unit of currency each time, and that we know that we're going to be paid we're going to either receive the unit that we wagered along with an additional unit back, in which case we won, and our count goes up by 1, or we've lost our wager, in which case it goes down by 1. So I'll start this at 0, and I'm going to have a for loop that says, well, I need to do n trials. So I can start I at 0, I is going to be less than num trials, and I plus plus. I is not going to serve really any purpose, since all we're going to do is call play craps once each time. And here's where I could say, well, let's play craps once and store the result of playing the game into a Boolean variable that's going to be called outcome. Okay, and I've gotten comfortable with this colon equals notation, but you'll recall that this really is that we're declaring a Boolean variable named outcome, and we're setting it equal to the result of playing craps once. And now we check, did we win or lose? And if outcome is equal to true, here I could delete the equal true, so I'm just testing if outcome is true or not. I like being very precise, especially at this stage of programming, and just saying, is it the case that when we played the game, we got a winner? So this would be a win. And there's nothing wrong with providing comments to yourself as you go through programming like this. So if the outcome is equal to true, then we won. What do we need to do? We need to increase our winnings by 1. Otherwise, well, in that case we lost. And so we should count minus minus, since we're going to decrease our winnings by 1. And that will keep track of how much money that we've won or lost each time. So we'll have a total amount at the end that we've either won or lost. And when we've done that, well, we want a house edge, which is an average amount won. So we want to return the average won or lost. And the house edge here if the value that we get is positive, then that actually will mean that the house has lost, that the player has won. But that's okay. We could take the negative of what we want in the end, and that's all right. So I'm more interested in the value itself, which is where we're going to return. The easiest thing to do would be to say count over num trials. And here's where we need to understand the particularities of the programming language that we're working in. So Go will interpret this as an integer division, and if we want it to be interpreted as a decimal division or an average, which is what it is, then we should typecast those to decimals and return the average as a decimal, which will match the return type that I told it as a float 64. And just like that, we're done. I've been steady with this, and I've provided plenty of comments, but we're only at line 73 of this, and we're going to have an answer to the question of what the house edge is. So I could go, for example, up to main. I've rolled my die. I don't need to do this any longer. I'm still going to seed it based off of the time because I want a different result each time. And now I'm going to set a num trials variable. I could set it equal to 1,000, or I could start it at a really low number. So we're only going to play 100 games of craps in the casino, and then I'm going to print, well, the house edge after we played the game num trials, and see where this gets us. Okay, so over in the terminal I could compile. I'm missing a return, so here Go often likes default values. Okay, so there's no way that we could make it to the end of this function, but Go doesn't necessarily know that on a compiler level, and so it likes seeing a default value at the end of the function just so that you're not forgetting in case you did have a default value. And so I'm not the biggest fan of this, but I could always write a comment that says something like, nope, panic, we shouldn't be here. And then, well, there's no way it's provable that you're not going to ever reach this line, because if I reached this line and I was at this line, in which case I was just panicking anyway, and so I'll just return this kind of dummy default value. But that will, at least for the purposes here, allow us to compile this and run the program. And so in this case, I was actually a winner. I played the game 100 times, and if I wagered $1 a time, then I won $8 as a result of the 100 wagers. I could let you do this. If we took the average of everybody who's ever run this program, then because the game is stacked in the favor of the house, we would see a negative number there. If I run the same program again, I don't need to compile. Here's what happened in my next 100 games. Well, in those I actually lost $18, so I would be down $10 as a net. I scraped it back up to only being down $2 on my next 100 trials. I could run it again. I made it positive again. You're starting to see the allure of gambling, but things are averaging out, and now we're going to stay negative for a bit. Although we did really well, and so it's difficult to see really what's going on. You know, you're going to get a lot of noise here, and so let's try running it for something like 100,000 trials. That's going to give us, and that should compile again. That'll give us a more accurate result. And so now we're at, on average, if I wager $1 every game, I'm going to lose 1.2 cents. So that's what that negative 0.012 says. I'm going to lose 1.2 cents for every $1 wagered per game. This is close to the correct value. So if I take it up to 1 million, then we're really starting to hone in on the correct value. Here I see negative 0.013674, and the house is starting to take over time. And typically when I have many people run the code on 1 million trials, then they'll see something in the neighborhood of negative 0.013 to 0.015, and we're getting around this true value, which is around 0.014. So on average, you're going to lose 1.4 cents per dollar per game wagered on craps, which is the answer that you could find if you are really interested in gambling and wanted to search what the house edge of craps is in general. So the house is always going to win, statistically speaking, especially when we go to mini trials. It's also a good way of featuring how quick Go really is. It's called Go for a reason. And so I could take this to 10 million trials, computing the house edge, and it takes us a few seconds, but it will give us an answer there that is starting to lock in on this 0.014 answer. So that concludes part one, where we wanted to compute the house edge of this game, and we understood how this worked on a pseudocode level, as well as taking the opportunity to delve into what is a PRNG, why is it that it's not truly random, what does it mean to seed a pseudo-random number generator, and why we care about things like this. Imagine forgetting or not knowing anything about this process and running this for 1,000 trials, not seeding the random number generator, and compiling and running, and we're getting the same number generation each time. So here, every time I run it, I'm going to think that the house edge is 6 cents when it's in fact 1.4 cents. Okay, so seeding, if we're doing Monte Carlo simulation, we should have that seed based off the current time. And here's why I explain what a seed is and what a PRNG is to begin with, so that I'm not just telling you to always put this line here, and so you have a true appreciation of what it means to seed a random number generation process. Okay, so that's end of part one. And part two will focus on returning to program our election simulator, using the same ideas that we've already explored how this works on the level of pseudocode. It's just a matter of converting it to the language of our choice. And I'll put this at the bottom, or excuse me, I need to go into the election folder, and I will close out, should save my main.go. And I'll just point out that there are a few files that are provided with the code. So, for example, I provided, I should delete this, that was me running it earlier. I provided an electoral votes text file, and that just contains the number of electoral college votes corresponding to each state. I've also got 3 .txt files, and this corresponded to us grabbing some polling data and taking an average of polls around a time in the 2016 US presidential election. So early polls.txt, that will have polls in the form of a state name and then 2 values that we're going to sum to 100. One is the probability, or the current polling percentage for candidate 1. The second one is the current polling percentage for candidate 2. Candidate 1 in this case was Clinton, candidate 2 was Trump. And so we have early polls that was early, several months before the election. We have a conventions polls that happened around the time of the presidential conventions in the summer. And then as the debates in the autumn happened, we have a different file that has those values as well. And there's no need to have the second number, because for each of these, the 2 numbers are going to add to 100. And in fact, I'm only going to access the first value because I can get the current polling percentage for candidate 2 for free if I just subtract the first number from 100. So there's some redundancy that's built into these files, although it does at least provide us with a check if we wanted to verify that the numbers seem to be reasonable. One way we could do so is to just ensure that the 2 values do add up to 100. I will point out, so those are the data sets that we're going to access. I don't want to make this about input and output. So I wrote some code already in an io.go file, io standing for input and output, that will do some reading from the file for us. So if you take a look at that, then we will see that it contains 2 main functions. And you could walk through this and I think have a good sense of how it is that each of these functions works. But it's a lesson in understanding that well-commented code will allow us to understand what it is that the function does without looking at any of the details of the function. So, for example, in this case, if we have a function called read electoral votes, it takes a file name as input. So it'll take, say, for example, electoralvotes.txt, and it's going to return a map of the state names to the number of electoral college votes. That map is going to be important for our work, since if a candidate wins a state, we need to access the electoral votes of that state and give that candidate the appropriate number of votes. So one way of representing this would be as a map of strings, so the keys are state names and the values are unsigned integers. And so from all that, we know how this function works. You could take a look at how it works. It needs to access some input-output package, range over the file, split the lines of the file into an array of strings, where each element of the string of the slice is a string corresponding to a line, and then it will read through the lines and do some string conversion where needed in order to produce the map that we want. And then at the end, the map has been produced and we return it. But I don't need to get into the details of that because we understand how the function works. The same goes for a read polling data function that's going to take in a file name, conventions.txt or debates.txt or earlypolls.txt, and then it will return a map of state names as keys to values that are the polling percentages for candidate 1. And as I said before, if we're assuming only a 2-candidate race, that's all that I'm going to need, because I'll get candidate 2 for free if I just subtract that from 100. In this case, it's going to be divided by 100, so the candidate percentages are going to be returned as decimals between 0 and 1, corresponding to the percentage for candidate 1. So those are the two functions that we have, and I have a little error checking function there where I make sure that if there's any process that any error that happens in this reading from file process, then I'm going to panic and end the program so that I can ensure that I'm getting, that I've read through the files and I've accessed everything in the file. So that's it. That's all I'll say about io.go. I want to focus on main.go, and where we want to actually do the process of Monte Carlo simulation for these polling data. So we have a function that we want to call that's called, simulate multiple elections, I believe I called it. And it will need to know the polling data themselves along with the electoral college map. And we also need to know the number of trials that we're going to run the simulation for, and we need to know the margin of error of the polls. It's another thing that we did. We are not building an industry standard election simulator. The idea is to see how powerful of a simulator we can actually build from first principles with probably a surprisingly small amount of code. So I would allow you, if you wanted to access all the polling data going back in time, to say certain polls are higher quality because they may have more respondents or they're historically more accurate. Certain polls have different margins of errors that we're going to just take an assumed value for averaging these out. We could be much more scientific about this process, but I want to focus on the programming side of things. So this function, which I called simulate multiple elections, is going to takes current polls, or takes polling data as a map of key state names to floats for candidate 1, along with what I said it needed to have a map of state names to the number of electoral votes, a number of trials to run the simulation for, and a margin of error in the polls. So I could convert that to say, well, it needs to take the polling data. That was a map of strings, which are the names of the states, to the percentages for candidate 1. It's going to need to take the electoral votes which is a map of state names to, I'm using unsigned integers because we will typically use integers, but this is at least a nice opportunity to use unsigned integers. We need to take the number of trials, and that really could be an unsigned integer as well. I'm just going to mix up the parameters here. And we're going to need a margin of error, and that's a value between 0 and 1, probably low. That's a decimal. And we need to say, well, what is it that it returns? It returns 3 values. And for the sake of redundancy, we probably should just return 2. The 3 values are the probability of, I should say, the probabilities or estimated of candidate 1, candidate 2, and a tie. So this is candidate 1 winning, candidate 2 winning, and a tie happening. Since it's possible that we have the same number of electoral college votes for each of the candidates. So I need to return then, if these are probabilities, 3 decimals. And so how this will work is we're going to keep track of the number of elections that are simulated, won by each candidate, and ties. So I'm going to have, let's say, win count 1 is equal to 0. I'm going to do a win count 2 is equal to 0, if I can get my syntax right. And let's do a tie count equal to 0. This is the oh no circumstance where the people have not chosen a winner, and so we have to go to another process within the government to choose a president. So at the end, way down here, I'm going to return the estimated probabilities, which means that I'm going to need to divide the win counts of each candidate along with the tie count by the total number of simulations that we've run, or the number of trials. So we need to say, well, I could just have a return statement here that was very long, or I could be very precise and say probability 1 is equal to win count 1 divided by the number of trials. And here, again, that's going to be interpreted as an integer division, so I should convert to a float 64, so it knows to do this as a float 64 division. And it would be dangerous to copy and paste, because I could do something, just a programming tip, I could forget to update this to a 2 and leave that as a 1. So those are the kinds of things we always want to be wary of. And so I could also have a tie probability, and that tie probability is float 64 of tie count over float 64 of the number of trials that we're running. And then at the end I would just say, well, I'm returning the probability 1, probability 2, probability tie. I mentioned that this is, I guess it's tie probability is what I called it. I mentioned that this is redundant because those 3 values are going to sum to 1. And if I know probability 1 and probability 2, I could get tie probability for free. You know, if there's a 51% chance for candidate 1 and a 48% chance for candidate 2, well then the tie probability is just going to be a 1% chance. After we take 51 plus 48, we get to 99, subtract that from 100. So I don't technically need this third value to be returned, but I'm going to return it just to be precise. So I should have the engine of what we do, and here's where we should start feeling comfortable that a very natural way of writing a function like this is to say, if we're going to simulate multiple elections, let's simply have a for loop that ranges over the number of trials. So simulate an election n times and update the counts, so each time. So we should have a for loop that says for I colon equals 0, I is less than the number of trials, I plus plus, and then within that I'm going to call simulate one election as a subroutine. And I could have simulate one election return perhaps the winner of the election as a string, or I could have it do 1, 0, or -1, depending on, we have perhaps 0 could be a tie, 1 could be a win for candidate 1, -1 could be a win for candidate 2. There's a lot of different ways of doing this. I'm going to return the two sets of electoral college votes obtained by each of the two candidates. So I'm going to have votes 1 and votes 2 be the outcome of simulating one election. So if I'm simulating multiple elections, I'm just doing this n times. And what that means is, well, I should pass everything that is going to need is everything but num trials. So I'm going to take the 3 parameters, I'm going to keep them in the same order. Polls, that's a map. Electoral votes is a map of strings to the number of votes for the state. And then I'm going to pass the margin of error down as well. I've removed num trials from the equation, and I've gone from 4 parameters to 3, and I've got a nice skeleton for the simulation. And now it's just on me to say, well, that's going to be the result of simulating an election. Did candidate 1 or candidate 2 win? And that's going to be an easy test, because we can say if votes 1 is bigger than votes 2, now we know that candidate 1 has won the election. So I'm going to increase the number of elections that they've won in the simulation by 1. Else, if votes 1 is less than votes 2, now I'm going to increase candidate 2's count by a single one. And else we have the dreaded tie, and we will increase the number of ties that we've encountered as part of the simulation by 1. Okay, so that is everything that we need for this high-level function to simulate the election n times. And now we just need this undefined simulate one election function. So I'm going to copy that function down and say we have a function called simulate one election. Remember what the types of these variables are. Polls is going to be a map of strings to decimals corresponding to the polling values for candidate 1. Electoral votes is going to be a map of strings to unts corresponding to the number of electoral college votes for a given state. And then we have a margin of error parameter that's a float 64. And then what this returns is the number of electoral college votes after one simulated election for each of the two candidates. And I can do that as ints. I could do it as unts. It doesn't really matter. Since these are votes, we may as well keep them as unts. And so now we need to simulate that election one time. So we will say, let's use college votes 1 is equal to 0 and college votes 2 is equal to 0. And these variables will hold the number of electoral college votes earned by the two candidates in one simulated election. And that's what we're eventually going to return. So I could be precise and say simulate one election takes a map of strings, state names to polling percentages, along with a map of state names to electoral college votes, and a margin of error. It returns the number of electoral college votes for each of the two candidates. And I could just return the number of votes for one candidate, since we know that the sum is going to be equal to 538, but that's okay. It'll return the number of college votes for each of the two candidates in one simulated election. So how will this function work? This function needs to range over all the states. And we're going to simulate the election based off the polling data on a state-by-state basis independently of each other. So we're going to simulate the election in each state. So we're going to need a for loop that will range over all the states. And the natural way of doing this would be to say, well, let's take all the keys ranging over the polls map that we have, mapping state names to candidate 1 percentages in the polls. And as we range over the states, let me grab the current polling value. So I'm going to grab polls of state, and that's going to be the current polling value in the state for candidate 1. And I may as well grab the number of votes in that particular state as the electoral votes of state as well. So remember, we've got two maps, and they each have the state names as keys. So if they have the same length and I'm ranging over the polls, well, that's the same as ranging over the electoral votes map as well. So I could change this to electoral votes since the keys are the same. I'll keep it as polls. So we have the polling value of the state stored in poll, the number of electoral college votes for that state stored in num votes. And now it's just a matter of saying, well, let's adjust the polling value with some randomization. Call it noise. And so I'll just say, well, the adjusted poll value is what happens when I take the poll and I add the noise using the margin of error. So the bigger the margin of error, typically the bigger the noise could be. And if the margin of error is very small, then the noise will probably be somewhat small. And so I've taken this adjusted poll. Now that's going to allow us to, perhaps we started with 52% for candidate 1, but that doesn't necessarily mean that candidate 1 is going to win, and the noise will allow us to bump that polling value in one direction or another. If somebody's at 52%, then odds are that they're in a good position to win, but we could bump that value down to be less than 50%, in which case candidate 2 is going to be favored based off of that simulation. So we're going to add that noise into the poll based off the margin of error, and now we check who won the state based on the adjusted poll. And that's a simple test, because we can say if the adjusted poll is bigger than or equal to 0.5, I will use bigger than or equal to. I could also use bigger than. In practice, the odds of hitting a decimal number exactly or functionally 0. If the adjusted poll is bigger than 0.5, then candidate 1 wins. And so if candidate 1 wins, then we should give candidate 1 the votes, the electoral votes for the state. And that's because all but 2 states have a winner-take-all system, so we're going to use this winner-take-all system as the simulation. And so that means we need to update college votes of 1 by adding to it the electoral college votes for the states. I didn't really need this num votes variable that's equal to the electoral college votes of state. I could have just copied this here, but I like being precise and thinking about, how it is that we're going to use this num votes later. So the other case then is, well, candidate 2 won. And let's give them the corresponding number of electoral college votes. So college votes 2 is going to be college votes 2 plus the number of votes for that state. And so we're going to do this over all the states independently. Each state will get a potentially different noise value added to it, because we might be wrong. We're kind of assuming that the polls aren't all biased in a certain direction, especially since the state polls are often operated independently of each other. And so we're going to run the simulation independently over all of the different states. So at the end of this process, we do 51 independent processes here where we add noise to each polling value each time. We'll eventually wind up with college votes for candidate 1, college votes for candidate 2, and that will be what we eventually return. Okay, so if I save this and compile, I'll get an angry message from Go because I don't have an add noise subroutine written. It's also angry at me because I have a type issue here. So I said I was going to return 2 uints. Well, college votes 1 is technically an int. So I should declare it to be a uint equal to 0. And this will allow college votes 1 and college votes 2 to be represented as unsigned integers as opposed to as integers. So now when we save it, we get one compiler error that says you haven't written the add noise function. That's great. So the add noise function is going to be where we build the randomness into our simulation. So it's going to take a current polling value. That's just a float 64. If you look at the polling value for the state, that's just the value of the polls map for the key state. So that value is just a float 64, the percentage for candidate 1. We will add, based off of that current polling value, we're going to add some noise and build in the margin of error. And in the theoretical lesson, we've seen how to do this. One way would be to assume kind of a uniform noise. It might make more sense in practice to assume something that's more centrally has a higher probability around the true polling value, and that then kind of diminishes going outward. So where it would be possible, for example, for a poll to say that one candidate had 52% support in a state, but in fact their true percentage was 98% based off of just the fact that we happened to ask a lot of people who were voting for candidate 2. And there are other aspects of this that would need to cause us to have noise as well. Perhaps people not giving a true opinion about the candidate they wanted to vote on. And so we're going to have an add noise function that has a polling value that I said was a decimal. And this is the polling percentage for candidate 1. We're going to have a margin of error, and that's a float 64 as well. And then we're going to return the updated poll, or the adjusted poll. And so I can say add noise takes a polling value for candidate 1 and a margin of error. It's going to return an adjusted poll for candidate 1 after adding random noise. And so we saw that we're going to use the standard normal distribution in order to build in this noise. And so, for example, I could say x is equal to, well, a random number from the standard normal distribution. So this is the distribution where if we select a number from it, we have an approximately 95% chance of being between -2 and 2. We have an approximately 68% chance of being between -1 and 1. You have this bell curve where things are probably closer to 0, so you have 68% chance of being within -1 and 1, but there is a possibility of picking a very negative value or a very positive value with diminishing probability, and the area under this entire curve is equal to 1. And so the probability of generating a number in a range of numbers is equal to the area under that curve. So this is built into Go as well. It'll be built into other programming languages. And here's where we're going to call rand.normFloat. And we will, so this number will be, if I divide it by 2, then x has an approximately 95% chance of being between -1 and 1. It started off with an approximately 95% chance of being between -2 and 2. If I divide it by 2, I'll get something between -1 and 1 with 95% probability. And then if I multiply this by the margin of error, then X has 95% chance of being between what? Well, I multiply by the margin of error, so negative margin of error and margin of error, which is really what we're looking for. So I have a value that I'm going to be able to add to the current polling value. So I'm going to simply return X plus the poll. And that will be the adjusted poll. So I'm going to have some noise where it's typically going to be between negative, if the margin of error is 0.05, negative 0.05, and positive 0.05, but this will allow me to have some noise so that if somebody's at 51.3%, it's certainly very possible for them to drop below 50% when we do the adjusted polling value. And so just as we saw before, now that I've returned X plus poll, I have an undefined rand, which is easy to resolve because I just need to import the math/rand subpackage. But once we save that, we're going to get something that compiles, I thought. It's norm float 64. Set a note there. So just as with other things, we specify that it's a float 64, but now we'll have something that compiles. Now it's just a matter of saying, okay, I've written an engine for this simulation, but I should also take care of what's going to happen in main. And the biggest thing that's going to happen in main is that I need to seed the pseudo-random number generator. So the first thing, let's seed the Prng. And I could open my previous file just to grab this line that I will never commit to memory, but just copy when I need, where I call the time package and access the current time on the level of nanoseconds. And so the Prng is going to be seeded, which will produce different results each time. So the same principle is at play here. Next, all we need to do is read in the two file names that we're interested in. So I could have, for example, I want to read in the Electoral college votes. And here's where, if I look at my IO package, or IO file that I've written, I have a read electoral votes function that takes the file name and that produces this map that I want. So if that's the output of the function, I could call this electoral votes. That's going to be the map. And if I read electoral votes, I need to give it a file name. So I could give it the file name that I know, which is electoralvotes.txt. And that will go in and read electoralvotes.txt and produce the map that we want. So I've read those in, and I want to read in the polls. And I could change main. We will see soon how to write a program that can take command line parameters and, depending on what the values of the parameters are, take different actions. So at the terminal, for example, tell it that we want to access debates.txt or earlypolls.txt or conventions.txt. I won't cover that in this lecture. I'm just going to have a file name variable, and let's start it at earlypolls.txt, and we can change that variable as we like every time that we run. I'm just going to need to recompile the program. Of course, I haven't used either of these variables, so I'm going to get an anger message when I save if I've got the compiler built in. And so when I read in the polls, that's going to produce a polls map of state names to candidate 1 percentages, and that's going to be reading the polling data based off of this file name. And so now I've got my electoral votes map, mapping states to number of votes in the Electoral College. I've got a polls map that maps the states to candidate 1 percentages. And now it's just a matter of running the simulation. We should have a number of trials, as well. And we should have a margin of error because those are the remaining two parameters that we're going to need to pass into the election simulation. So the number of trials that we could run, we could start this as something like 1,000. And a margin of error, maybe we allow for a 5% margin of error in our polls. And then at the end of this, we're going to, remember it's been a while, but we have to simulate multiple elections. And it returns three values, the estimated probabilities of each of the two candidates winning, as well as a tie estimated probability. So if I call simulate multiple elections, I'm going to have a probability 1, probability 2, and probability tie are what's going to be returned by this. So if I call simulate multiple elections, it's going to take in polls, electoral votes is this other map that we've read in. It will take num trials, and it will take margin of error. Okay, so I've just hit tab there to advance it. And if the variable names are the same, then everything will be ready to go. Now that we've actually done the simulation, it remains for me to print out some nice output to the user. So let's say something like estimated probability of a candidate 1 win is, and probability 1. And I'm going to copy this. And the estimated probability of candidate 2 winning is going to be probability 2. And then the estimated probability of a tie is the probability of a tie. So I get an unexpected probability 1. Nope. That's because this is such an easy mistake to make. I forgot to put my comma outside the string, so I was printing this string including the comma. But that's an easy one to debug because it says I was not expecting probability tie, and that's because I didn't get to see the comma that says print it out separately. So the PRNG has been seeded. The simulation has been run after we've read in the data from the files, and so it's just a matter of actually running our simulation. My terminal is currently in the previous craps directory, so I'm going to cd ... to move myself one level up, and then if I cd down into election, I'll be in the election directory, and I'll be ready to compile the code. And we're going to run this for 1,000 sim trials. Let me make this a little bit more reliable. So we're going to run 100,000 simulations, and hope everything goes well. So wish us well. I hope that everything is fine. I've got an extra print statement. So I've produced in io.go. I think I must have, yeah. I've got an unnecessary print line statement from when I was just ensuring that everything was okay. So we can remove that and everything should be fine. We won't get these extra prints. This is just printing the number of electoral votes for each state so that we can see that. And we can see that at least we can see that we've read it in correctly. And then here we see that the estimated probability of a candidate 1 win is, it wraps around the next line, 0.99893, and that the estimated probability of a candidate 2 win is 0.00089. So here candidate 1 is Clinton, candidate 2 is Trump, and in the early polls with this 0.05 or 5% margin of error, which we've seen on the level of simulations, means that if we're assuming that we're within 5% of that polling value with 95% certainty. So if we assume that 5% spread for the most part, then we're seeing a substantial estimated probability of a candidate 1 win. I could up this a little bit because, 5% is a pretty reasonable margin of error. But let's see what happens when we take it to 0.1. And so I'll need to compile again and run again. This is the benefit of using command line parameters, because the program would have already been compiled and I'm just changing the parameters that I'm passing into it. But we'll do that soon enough. I just want to see the result here. But even with a 10% margin of error, meaning that somebody could be at 60% in the polls and there's still a 2.5% probability that we're going to give that state to the other person, even in this case, we see a significant polling advantage to candidate 1, or Clinton in this case. I could change this and say, well, maybe it was just an early lead in the polls. So we could look at the different polling values that we produced. So this was for conventions.txt, and see how that changes things. So here we had a 98.7% chance estimated of a Clinton victory. If I change to what's going on around the times of the conventions, I'm actually, in my case, and I would bet that your values will be similar to this, I'm going to get a 99.3% estimated probability of a candidate 1 win. And I could have a more reliable simulation if I ran this for not 100,000 simulations, but for 10 million or something like that. But actually, the 538 folks, I think, only ran their daily simulations for 10,000 simulations or tens of thousands. And so here we see it actually looks like a more decisive potential Clinton victory for these data. And we could even look at then, well, the last set of polls were taken around the debates. And so here, if we compile and we run, when we simulate, we see we still have an even higher. Now for this, at least for my end, I get a 99.5% probability of a candidate 1 win. You can see those presented a little bit nicely if we just expand the terminal a little bit. So the question becomes, what's going on? And we're going to move from part 2 of the lecture to part 3, where we have built something and we want to step back from it and analyze it a little bit and think about the nature of what it is that we're doing when we're simulating an election via Monte Carlo simulation, and trying to use that to forecast an election, especially because I mentioned that we're not trying to produce an industry standard simulation, but it's still quite different from both 538 and the New York Times. If you remember the plots that I showed, they had maybe a 70% probability of forecast probability of Clinton victory, or an 85% forecast probability, but they were never as certain as 99.3% or 99.5%. And this might strike us as odd because 10% margin of error is quite significant. So how is it that our simulation would compare against something that's published? And then let's step back and think about the nature of forecasting an election from polling data to begin with. So I've got a few slides on this. Normally I'll separate out the theory from the practice, but I think in this case it's worth pointing out a couple things about election simulations. And here was me running it previously, and I have a table that's very similar to what we have, and we realized that it's not at all like what the real simulators saw. So they were much more conservative in estimating the probability of victory of one of the candidates. And so what is it that they might have done that we didn't? There are a few things that we didn't do. One thing was that we didn't grade polls. So a very nice thing that the 538 outlet did was to say, well, some polls are traditionally unreliable. They may be skewed very heavily in one direction, or they may have a very low number of respondents. So this Research 2000 tends to have a Democratic slant, or the Rasmussen ones tend to have a heavy Republican slant, and so they get low grades as a result. But Survey USA, they said, does not seem to have a lot of bias traditionally in that poll. And so we're going to give it an A, so we could maybe weight a polling value more heavily based off of one poll or another based on its quality. We are seeing a very heavy prediction for candidate 1, in part because we're using a normal distribution that doesn't have quite such a fat tail as what's often used in practice, which is a t distribution. So it will have a higher likelihood of a more extreme outcome And this is in an effort to reflect the fact that it's very difficult to say, based off the polling value, if we're 2 months out from an election, what the true polling value is, or how reflective that is of how election day is going to proceed in 2 months' time. So the fatter tails, where the blue distribution here on the right is a T distribution, and depending on, you can change T essentially, and you can get kind of fatter tails or skinnier tails. But we could if we have fat tails, then it's going to be more likely, because we have more area under that curve, of getting an extreme outcome when we add the noise. If you think about it, this wouldn't change our simulation a huge amount. We could write a different add noise function that's based off of a T distribution. Perhaps it takes T as a parameter, and then it produces an adjusted poll, but everything else about our simulation is the exact same. So this is, again, seeing the benefit of modularity in programs that have very clear subroutines or very clear functions that call each other and have very clear input and output, and that aren't very long, that it often will allow us to change our code and produce something that's very different with a minor change. In practice, though, there's a big correlation between state voting. So, for example, Minnesota will tend to be correlated with Wisconsin. Other states won't be very correlated with each other, but you may think, well, if these states are similar geographically and they have similar voting patterns, and there's something behind the scenes that's causing the polling data to be off in a certain direction. Well, odds are that they're going to be off in the same direction for those two states. So if another way of viewing this too is that if two states are heavily correlated, but we have treated the add noise function as independent for those states, it doesn't make a whole lot of sense for the add noise to increase the number of votes in one state, or increase candidate one's percentage in one state, but then possibly decrease it in the other state. Typically, if one state goes up over the estimated value based off the polls, the other state is typically going to go up as well. Our simulation treated those two states as completely independent. And so as a result, we get wound up with something that doesn't reflect this actuality. And we could build that into the simulation, though, as well. So you could imagine that we might pick certain states randomly, for example, and then add the noise to polling values of other states based off of this correlation that we saw. Again, it's a very practical idea that, in the grand scheme of things, probably wouldn't add that much to our code. There are other polls that were run, though. So there was a Daybreak poll that was run by the LA Times, and the quote here was that their questions allowed voters to express a greater level of certainty or greater level of uncertainty than traditional poll questions. So a traditional poll would say, which candidate are you voting for? And that's a binary response, candidate 1 or candidate 2. But in the Daybreak poll, the respondent might say that they were 60% for Clinton and 40% for Trump, or 90% for Trump and 10% for Clinton. And we could pause for a moment and say, well, that seems like a good idea. Doesn't necessarily make it a good poll. And interestingly here, too, you'll see that based off of the uncertainty, if we weight the enthusiasm of the respondents, then we see that Clinton actually only very rarely was in the lead in 2016 in this poll. If we weight based off of enthusiasm and infer from that that Trump supporters were more enthusiastic on average, then we saw this 46.8% to 43.6% as the final number. It doesn't necessarily make it a good poll just because it had a final number that wound up reflecting the election. I pointed this out in the theory lecture, but we could have a perfectly reasonable forecast that had 90% for one candidate and was just wrong because it would have been wrong 10% of the time anyway. So this does not necessarily make it a good poll. The other thing that's problematic about it is that it was a national poll, which as we've seen, it tends to be better to use state-by-state polling anyway, rather than using a national poll, since as we saw in 2016, it's possible to win the popular vote or win the majority of votes across the country, but not win the election because the election's based on an electoral college. One more thing I want to point out here is look at the volatility in the forecasts that are produced from the polls. So it's the volatility in the forecasts, but it reflects the volatility in the polls behind the scenes, where people are changing their minds, or the polls themselves are bouncing around a lot. And I always ask my students to stop for a moment here and think about, if a weather forecaster told you that there was, in 3 months' time, a 70% chance of rain, to consider whether or not you would believe them. What would be a fairer probability for what the chance of rain is in 3 months' time from today, rather than 70%? Especially, say, you live in an area where, on average, especially that time of year, it tends to rain on 15% of the days. Wouldn't you think that that forecaster was kind of over-expressing their certainty in a number of 70%? It would be very untrustworthy, okay? And what I'm trying to get at there is that a lot can happen in 3 months' time. These polls reflect an ongoing election where information is changing, where candidates are presenting platforms and so on. And the polls in July might reflect the state of an election taking place in July, but it's difficult to infer that they reflect much about an election that's going to be happening several months down the line. There's an interesting connection of volatility if we look at a place where volatility is very prevalent, in the stock market. So I always ask my students to tell me which of these two stocks they would rather bet on as increasing 30% in the future 6 months. And these stocks were captured in 2017, but it wound up being an excellent example, so I always come back to it. And I ask students, which of these would you think, if you had to bet $1 on this and somebody was going to give you a payout based off of the result, so somebody was going to give you your dollar back plus $3 more, which of these stocks you would rather have your money riding on as increasing 30% in 6 months? And you can see here there's a plot of time on the x-axis to the value, or the stock price on the y-axis per share. And many students will look at the plots and say, that top stock has gone up steadily in the past few years. But I like the scientist's answer that the bottom stock is more volatile. All right, especially because if I'm betting on a stock increasing 30% in 6 months, and I know that a stock in the past has not been very volatile, volatility is what I need in order for this bet to pay off. So I want a more volatile stock will typically be more lucrative in that circumstance. So if I had the choice between the two, I would pick the volatile stock over the one that has had steady growth. And I could check in on them 6 months later. This was just, I picked two stocks, one that had low volatility, the other that had high volatility, and I had my fingers crossed that something nice might work out. And this is why I've never changed the example, because the top stable stock, it went up a few percent, and everything was fine. And this is for a larger time window, so we were originally at like 66 for that top stock, and 6 months later it wound up going to $73 per share, so it went up a little bit, but not 30%. The bottom stock was actually a winner. It went up to $45 a share. Then it actually, after that point, went even higher, much higher, almost up to $80 per share. And then it went much lower and had a dip. Since that time, it's had another dip. And I'll just tell you that the top stock is Colgate-Palmolive, so they make stuff like toothpaste and cleaning supplies and things that wind up being pretty stable over time. But the bottom stock is First Solar panel company, and that's a market that tends to wildly fluctuate based off of market conditions, who the current president is, laws that are passed, subsidies, that kind of thing. And so the stock price can kind of rocket up and rocket down based off of speculation and what people think. Interestingly, we could think about examples of these prediction markets where investors can speculate on what they think might happen. And there's been notable examples of those having gone wrong. So after September 11th in the US, an idea was floated that, and it became reasonably close, I think, to actuality, that we would have a terrorist future where investors could speculate on what they might think would happen with respect to major terrorist events. So they could perhaps predict that one was very likely, and they would actually receive a payout if a terrorist event actually occurred, if they were wagering on that. This was scrapped kind of at the last minute, perhaps for good reason. But there was even a prediction market for the 2016 election. The LA Times ran one of these. So not only did they have that Daybreak poll where you could express enthusiasm for one candidate or the other, they asked people, who do you think is going to win? Not how enthusiastic are you about a candidate, but what would you predict? And not who you're voting for, but who do you think is going to win? And here we saw a more narrow lead for Clinton throughout the entire process, but it wasn't as wide as 99.6% that we had, or it wasn't as wide as 85% for New York Times or 70% for 538. It was a lot more narrow. Of course, there's weaknesses with that as well. If you support a candidate, then odds are you're not going to be the most unbiased observer in terms of who you think is going to win. There actually already is a prediction market for stocks, and it's called the market. So the derivatives market is, no one really even understands how big it is. It's certainly in the trillions. On the high end, there have been estimates that it's as large as $1 quadrillion. And these are opportunities for us to invest on, not on assets, but on things that are attempting to price underlying assets. So a derivative is, say, example, if it's a stock that's the underlying asset, we're making an investment, but the price of the derivative is tied to the value of the underlying asset. So the example that I gave before of you making a bet on whether a stock would go up or down is an basic example of a call option. So for example, if a stock were trading at $60 per share currently, and we wanted to we could make a bet that if in 6 months time or 3 months time or however long it's above $85 per share, then if it's at $100 per share, then we would receive the difference in 100, and that what's called the strike price, $85, we would receive $15 for every dollar that we had wagered. Okay, and so what's interesting is that options on stocks, they price in the volatility. The more volatile a stock has been, the higher the price if you're going to try and pay for a call option, hoping that the stock is going to go up. Colgate-Palmolive, if we looked at it at a given time, it was at about $70 per share, and we were thinking about it going up maybe around 20%, then the cost of one of those call options would be about $1.50. If we looked at instead that for solar, and we looked at the same type of general growth, you have a much more expensive call option on that stock, because since it's bouncing around and it's so volatile, it may just be that at that time it's bounced upward, and so you would have made a lot more money, since at the end of the day, if the stock goes down, in either case you're going to wind up just losing your original dollar. This sounds like it's not connected to election predictions, but it was proposed as a potential way of simulating an election and making a forecast. So there was a notable example from Nassim Taleb where he called out the 538 simulations, not for being a fun thing to program, but for claiming that they were probabilities, for claiming that they were accurate forecasts. That if you have a probability that's claimed as 55% for Trump on one day after he speaks at a national convention, and then 10 days later after Clinton gives an interview, it's a 20% swing or a 30% swing the other direction after just a week or two, then there's too much bounce, there's too much stochasticity in those for them to be claimed to be a probability. It's the same thing as if you checked a weather app on your phone and it's telling you one day it's an 80% chance of rain in 3 weeks, and the next day it's a 10% chance of rain in 3 weeks. We would start to question the reliability of that. So the idea was to try and build in an election simulation that used the option pricing models, taking what we already have done for decades on the in the marketplace for derivatives, and comparing that and kind of building it into an election forecast. And so in such a model, you wouldn't have really any certainty that it was going to rain in 3 months' time, and so everything, an election with two candidates would hover around 50%, and then you would get much more confident in one direction or the other direction the day before or the day of the election as you started to see your polling data, and then as the election happened at the end, you would be 100% for one candidate or the other. So if you, in the option model, the blue lines kind of hover around 50%, and then they jump one direction or another. It was at least an interesting idea. And you know, the other thing to point out is there actually is an election market too. If you want to make a wager on who's going to win the election, if you think that the market is an accurate reflection of election forecasting, here's the odds checker of different betting houses in the UK in September 2018. And we could see that, and there are quite a few very interesting potential wagers that you could make. So for example, you could wager on Dwayne Johnson or Dwayne "The Rock" Johnson. Some of the bookmakers had those as two different things, or Jeff Bezos, or Jesse Ventura, or different very random people in September 2018. And the elections will change from September 2018 to September 2019. Trump, for example, went from a 2-to-1 candidate, so about a 1 in 3 projected chance according to the market, to about even odds, or the same example as what we had with craps. $1 wager would give you your dollar back plus an additional $1, and the odds for the Democratic candidates had kind of changed over that time too. Of course, we could stop and reflect here and say, why might a gambling market not offer an accurate forecast? And there's a number of answers there. One would be that the people who gamble in a population are not necessarily an accurate subset of the people who are going to, or an accurate proxy for the people who are going to actually vote in the election. So you could just be honing in on what gamblers think about this particular candidate, and that might be biased in one direction or another. Another more subversive one that people might not realize at first is that what would happen if one candidate had more total wagers placed upon them, but the other candidate had more total money placed upon them, which is exactly what happened in 2016. The total amount of money wagered was more heavily in favor of Clinton, but there were more wagers placed for an average lower amount on Trump. And so the odds were adjusted based off the total money, not realizing that one candidate had larger average bets placed upon them. The exact same thing then happened with the Brexit referendum, where there was more money placed on Britain remaining within the EU, but more bets were placed, albeit for smaller amounts on average, on the UK leaving the EU. And so that was invisible when you just saw the odds, which were adjusted based off of average amounts wagered. So there are a lot of things to be concerned about even a simple election simulator like we produce, and trying to look at how this is done in practice. And I think there's a bigger moral too, which is that, you know, Monte Carlo simulation is really cool. We did 2 applications in about an hour and a half, and we could use these to build out really nice data. And you look at the 538 plots, and they're all very pretty for this type of thing. Here's one that's based off of, you know, giving states different sizes based off of their population, where kind of each hexagon is one electoral vote. And we see a really interesting picture of kind of the shape of the U.S. based off of population and how they're voting at a given time. And then we color them blue or red in different shades based off of how far ahead one candidate is in a different state. And that's all very well and good. But if we step back from those types of really nice, very pretty things, we still need to continually question, pick apart what we've done. Why is it that what we did wasn't necessarily a great forecast? But then also step back even farther from that and talk about the nature of forecasting an election to begin with, and make connections to other things. You know, you wouldn't necessarily think that something like the derivatives market might provide interesting insights into the nature of our simulation, but those are the types of things that we do in science all the time. I guess when I think about the course being for lovers, that's part of the spirit of it, that, you know, the election, an election simulator is just as interesting to look at as understanding how the derivatives market works and looking at this weird prediction market for terror futures and that kind of thing. So that's the end of part 3 and the end of our objectives for this lecture. I thought it's always one of the more fun things to do because we're able to build something in a relatively short amount of time and understand Monte Carlo simulation and the nature of pseudo-random number generation on a pretty significant level. And so I thank you for joining me, if you were able to make it the whole way, and I look forward to seeing you next time. Thank you.